Hello, we are looking at probability. We're looking at how to solve probability problems using diagrams and formulas. There's our learning intention. Now, I think you have met your learning intention and you'll have success in your learning if you start using Karnaugh maps and probability tables to solve problems. And you can draw on the addition rule for determining the union and intersect of events, and you can use a tree diagram and the multiplication rule to solve problems when you're looking at conditional probability. Alright, let's go. So we're going to start off just reviewing our ideas about the Venn diagram and our addition rule, and then we're going to look at some new ideas about how to interpret some probability problems and how to set up a Karnaugh map to help solve a problem, and then look at a tree diagram problem. Okay. So, in this situation, let's just say we're rolling two die and we're going to record the sum of the scores. Okay, so the score is the top number on top of the face. Alright, so how many different ways do you think you can achieve a 7? Well, you can roll a 3 and you can roll a 4, you can roll a 5 and a 2. How many times are there? Maybe a 1 and a 6? Well, you can also do the other order as well. Maybe the 6 can come first and then the 1. So altogether we have 6 different possible outcomes. So there they are. Alright, so then how many different possible outcomes are there for rolling two dice? So that's all of them all together. Well, I've got 1 to 6 on one die, I've got 1 to 6 on another die, so combining them two together, 6 lots of 6, okay, is going to give us a 36, and we can help to determine that by drawing what's called a lattice diagram. If we get 1 to 6 outcomes on one side, 1 to 6 outcomes on that side, and we form an array, and we can see there's 36 possible arrangements in our array all together. Okay. Now, if we know those two ideas, how can we then determine the probability of achieving sum of 7 from rolling two die? Well, the whole idea of a probability is the number of outcomes we have of the desired event we're looking at, such as the sum of rolling a 7, divided by the total number of outcomes altogether, which is our 36 outcomes in our sample space. So there we have it, the number of outcomes of the sum of 7 divided by the number of outcomes in the sample space, and it gives us this proportion. Always simplify your fractions. So 6 into 36 goes into themselves, and we see that we get 1 out of 6 as our probability. Not too bad, huh? So there's a nice simple probability problem there. As a quick review. Now, let's think about these two diagrams. So when we use diagrams to solve problems, we need to have an understanding of the diagram and the different regions of the diagram and what they mean. So here's our Karnaugh map and our Venn diagram. As you can see, they're both two events. Karnaugh map allows you to clearly see all 4 possibilities where you have the event A and its complement, and the same for event B. So the first part is this region. This is the intersect between A and B on the two diagrams. Here is the other region where it's A intersect with not B. And then this region, which is not A intersect with B. And then on the outside here in the Venn diagram is the same as this region here, not A intersect not B. Now you have these parts of your Karnaugh map. Now, what's important is that all the columns and the rows must add to give you the outside value. So this part plus this part adds to give you A, all the outcomes in A, and so on. Whereas all the row at the bottom and the column at this far right here, they must add to give you your full sample space. Okay, so this is a useful tool in helping you to work out the probabilities of events. Now, on top of that, we can easily apply the addition law of probability. So here it is here. We've looked at this before. This says, what's the chance of event A or event B occurring? and it's given by this addition law of probability. Probability of A plus B minus the intersect. Okay, so let's look at a problem. So a particular university, the probability that an art student studies a language is 0.3 and literature is 0.6, and both is 0.25. Okay, so from that, here goes my little arrow. I'm going to help us to read about it. A student studies either a language or literature. Either or a literature. Okay, so first off, what's important is to identify the events that are occurring. We've got two different events. Studies language is one event, and the other event is studies literature. And so a karnaugh map is useful in this type of problem, where we have two events that can happen at the same time. So we've defined and set up our karnaugh map and defined our events. And then from that, we have our information that we've highlighted in the question, and I've placed it in the appropriate spots. So you can have a little think about that if that's suitable location. Now we know that we have a probability of 1, which is considering all outcomes in the bottom corner. Now, from next thing is, remember the idea that the rows and the columns must add to give you the outside values. So I have 0.25 plus another 0.05 is going to give you a 0.3. And adding this row, this missing probability must be 0.35 for this to add to 0.6, and so on. And we can work out the last one there. That's last missing probability. 0.35 would be that result. So let's answer the question. A student studies either a language or literature. Well, that is this probability situation. Language union with literature. So this is language or literature occurring. And we use our addition rule. There it is. And so each part of the rule we can identify them from. Okay, so now let's think about part B. So let's say a student studies neither a language nor literature. How do we interpret that? Neither a language nor literature. Well, it's like a double negative, isn't it? So it's like not a language, not literature. And that is happening together. Okay, so we want to think about that as a no language and a no literature happening together. So it's an intersect of land complement, intersect literature complement. Okay? And that is this point here from the karnaugh map. It's this probability, the 0.35. Alright, so whenever you see a neither nor statement about events, that means event complement and no event complement. Okay, very good. So that's how we use our karnaugh map to solve some worded problems involving intersects. Now we're going to consider this scenario. Let's say we've got coloured balls that are just random in a box. Okay, we've got some blue balls, we've got some green balls, and some pink and some red. We're going to randomly draw them out. So let's say if a ball is chosen at random, what's the probability that it's a blue ball, for instance? There one is. Okay, well, how much do we have? That's how we can write it as a probability statement. So we can see we've got 4 blue balls out of a total of 12, so that's a third. Okay, what about if we think of it like that? Let's say we draw a blue ball out first. Now, given that a blue ball was drawn out first, now what's the probability of drawing a blue? Well, since the blue ball has come out, let's have a look at what's left in the box. We've got 1, 2, 3 blues out of 11. So probability has changed, hasn't it? 3 out of 11. Well, that's different now, isn't it, than just our 4 out of 12 or a third. So in the situation where another event happens first or some condition is given to us that affects the probability of an event in the future. Okay, so that's the scenario of conditional probability. And conditional probability, usually if you're given a statement like this, say for instance, given that a red ball is chosen, what is the probability of drawing a blue? We can express that in a probability statement like so. Okay, this says the probability of blue given red. Okay, so now you think about if a red has come out, we've got 4 blue out of a total of 11, and there's our probability there. Okay, so conditional probability, probability of event B given A. Then how do we think about that in an equivalent formula? So let's look at our Venn diagram. So let's say that event A has occurred first. So given that event A has occurred, then that encompasses all this region. Now we're interested in, given that A has occurred, what is the outcomes of, what's the chance of event B happening? Well, event B, given that A has occurred, is just this little region. It's the intersect. Okay, so there's B. There's this region here. Given that A has occurred, you're just thinking about the intersect. Okay, so we consider the intersect of A and B, that out of the chance that that probability of A has occurred. So it's intersect divide by the probability of A. There's an equivalent formula for conditional probability. Now, from that we get our multiplication rule for probability. By multiplying by the probability of A to the left hand side, we get an expression for the intersect of two events. A intersect B is given by this. Okay, now that's interchangeable. It could be B given A times probability of A, or A given B times probability of B. They are equivalent and they're interchangeable. They both give you the same intersect probability. Okay, so it's an important thing to remember because you may need to relate these two forms together. Now, in the case where we have independent events, that's where no conditional probability applies. Okay, that says that given that A has occurred, that does not affect the chances of B occurring. That's because A and B are independent. So B given A is the same as just the probability of B for independent events. So how does that affect our multiplication rule? Well, the intersect is just now probability of A times the probability of B by itself. There's no conditional probability anymore. Alright, so that's another important definition and the situation, how it will change for independent events. Very good. Let's consider solving a problem involving conditional probabilities using a tree diagram. A tree diagram is a very important diagram that is most useful for conditional probability type problems. So this is important for situations where you've got two events, where one event might occur first and it might have an influence on the second event occurring. So you've got event A and event B. So the two possible branches for event A is A occurring or not A occurring. And then after that is a situation for the second event, event B, you've either got B occurring, given that A has occurred, or not B occurring, given that A has occurred. And the same kind of situation, but when not A has occurred first. So that's the structure of a typical tree diagram. Now, using our multiplication rule, the intersect can be determined by multiplying the probabilities of the first branch times the second branch. Whereas if we're saying want an intersect such as not B intersect not A, well, that's these branches that are multiplying. And you can see how it fits in the rule. Okay, so the tree diagram can be very useful for determining the probabilities, say, intersects between events. Okay. So now let's see how we can use this tree diagram and put it together in a problem. But before we go with that, let's think about the situation. What happens if we just want to ask this question? What's the probability of the second event B occurring? Only that one. But B changes depending on what happens previously, depending on what happens if A. Probability of B is different if A happens, or probability of B is different if not A happens. So let's think about where in the tree diagram is just the probability of B occurring. Well, we have it in the top part there, and we have it in the bottom branch here as well. So that's where B occurs, and it exists in two parts, when given that A has occurred and given that not A has occurred. So we're going to combine them two. And it will be in the situation where we have the multiplying of the two branches plus, and then the multiplying of the next two branches. So we get this combined multiplication rule. We're going to call that the law of total probability. Okay? And it allows you to determine the probability of just a single event depending on conditional relationships of the two events occurring together, A and B. So in Melbourne, the probability that it rains on any Monday is 0.21. Now, if it rains on a Monday, then the probability that it rains on a Tuesday is given by that number, 0.83. Now, if it does not rain on Monday, then the probability of rain on Tuesday is 0.3. Find the probability that it rains overall on the Tuesday. Now, first off, let's define the event R. R, we're going to say, is when it rains on a day. Alright, so we've got R1, which is Monday, and R2, which is Tuesday. Now, let's summarize these descriptions in the question with probability statements. So the probability that it rains on a Monday, which is R1, is 0.21. Now, if it rains on a Monday, so it's given R1, then probability of R2 is 0.83. And then we have this one, probability of R2, given that not R1 has occurred, because it did not rain on the Monday. So let's find the probability that it rains on a Tuesday, which is just R2 only. Now, using the law of total probability and helping us with a tree diagram, we can work this out. So there's our tree diagram in terms of whether it's raining or whether it's not raining on a Monday or a Tuesday. And you can see all the four possible branches there, four possible occurrences. Now, that's the information that's given to us in the question, so we can assign it to the branches we see. Now, what's important to think about is that the probabilities of each branch pair, they're going to add up to 1. So this branch and that branch there together are a branch pair, and the sum must add to 1. So we can work out all the unknown, the probabilities, or the other conditional probability events. There's our law of total probability that we can use to work out probability of R2 when it rains on a Tuesday. And by identifying the parts from our tree diagram, we can get our numbers in the right spot and do our calculation. And there it is, 0.4113 to 4 decimal places. Okay, so we can answer conditional probability questions like that might seem complicated, by laying out the information carefully in a tree diagram and using an appropriate formula. Okay, now we're going to stop there, and I want you to think about how you can use a Karnaugh map or a probability table to answer certain problems involving intersects, or how you can use a tree diagram to answer problems similar to this involving conditional probability. Thank you.